the Omron portfolio or the Sysmac portfolio, but I figure a 5-minute refresher can't hurt. So we're in session 1 today. So we're going to be doing setup and programming basics. I'm just going to do a quick run through of kind of who is Omron. You guys probably know us. We've been around in the industry for it's almost 90 years now. We're about a $7-8 billion company. We've got offices all around the world, 36,000 employees worldwide. 40% of our revenue is all based around industrial automation, and we do a large reinvestment into R&D. So we're coming out with new products, a lot of new innovating things year over year. So keep an eye out for that. So today we're going to be talking about Sysmac. Sysmac as a term is kind of an overarching term. So in the Sysmac lineup, we can classify that as any of our safety equipment, safety controllers, safety hardware, sensors. And then this is probably the area you're most familiar with, is the control side of things. So controllers, IPCs, HMIs. We've got robotics, servo control. That falls under the Sysmac platform as well. And then kind of the supervisory area. So we can kind of classify this all under that Sysmac umbrella. And today, right, the development environment. So that's going to be Sysmac Studio. So that's what this course is all about. So what is Sysmac? Sysmac is a term coined from Omron. It's the system for machine automation control. So machine automation control, it's kind of a term combined from multiple areas. So traditionally, you've got DCS systems, you got PLC systems, you got process automation controllers, PACs. In the Sysmac lineup for Omron, we've kind of put all those together. So you get your motion control, your advanced motion, your vision integration, your basic PLC functionality, and then we also integrate kind of the DCS side of things. We're not a DCS system, but we have the capability of doing very large-scale systems with networking and all of that kind of stuff incorporated into a machine automation controller. So this is the lineup of our controllers. So when we look at this side of the page here, we're looking at Sysmac Studio. So on the left-hand side, that's all stuff that's going to be programmed with our CX1 software. We are looking at the Sysmac Studio side of things, so the latest and greatest. In 2018, we came up with our NX1 controller, which is kind of probably what most of you guys have come across. It's probably the most cost-effective and capable controller in our lineup. And, we've got EtherCAT, Ethernet IP built right in. We've got versions that have SQL integration. They come standard with OPC UA communication. So we've got a lot of cool things with this, and it also does motion and can incorporate a lot of other aspects. So we've seen this be a very profitable controller on the Omron side, and for sure it's helping your businesses kind of move forward with either machine builds and all that kind of stuff. So it's a very capable controller. So EtherCAT, I'm not sure how many of you guys are utilizing this, but we base a lot of our technology around EtherCAT now. So it is, I believe, the fastest network out there right now. We don't need to go too much in depth on this, but EtherCAT is one thing that a lot of the focus is going to be on, and it's definitely changing in the market to be more surrounding EtherCAT instead of Ethernet IP or Modbus. Easier, faster setup, faster speeds. So yeah, you can incorporate your I/O, motion, vision, safety, all under the EtherCAT network. So on that, we also have the world's first supporting distributed safety network controller supporting safety networks here. So you can have Ethernet IP and EtherCAT networks kind of working alongside each other. You can't interpose them on the same network, but you could have your existing control platform, having your Ethernet IP communications between certain devices, and then you can have a sub EtherCAT network controlling safety, and all that comes back to kind of your cloud network. I had mentioned OPC UA, so that's one thing that comes standard on the NX1 controller and a handful of our other Sysmac controllers. So we don't need to go too in depth on that, but just know that OPC UA is a standard function, and it's one thing we see a lot of people gravitate towards And it's really easy to integrate. I'm sure we might get into that on this course, or at least graze that topic. So with the I/O, we integrate our slice I/O right onto the NX series controllers, and then we can also utilize this for remote I/O. So we've got a pretty large network of I/O devices, or sorry, I/O cards. So everything from just basic DIDO, AIAO. Then we also have I/O link masters, servo control. You've got your safety cards as well. There's a lot of things on here. It's a pretty large portfolio of cards. Here's a pretty good example of a remote I/O network that incorporates both basic I/O and safety I/O. So anything that's labeled with the red or is physically red is safety. So we've got EtherCAT and Ethernet IP options for the remote couplers, and they all communicate directly over that NX bus is what we call it. So you can do up to 63 units per coupler. So you can build a pretty substantial network out of these. And we integrate into third-party control systems. So if you just want to utilize the NX-IO for that, we have that capability. So kind of getting into what we're talking about here. All of this stuff can be, most of this stuff, I don't want to say all, majority of this stuff we talked about here can be programmed through Sysmac Studio. We like to follow the line, one controller, one software, one connection. You don't have to bounce around through different softwares. It's all incorporated into one. One-time purchase. We like to say that we're a hardware company. We don't push software like some of the other competitors out there. You receive lifetime updates for the lifetime you have the software. We've got technical support. Like I said, we've got PLC programming, HMI programming, and motion, plus a lot more all in one platform. And it's a very intuitive software, easy to navigate, and we're gonna find that out. So, yeah, let's get to it, Stu. I know it's we got a busy day planned, so we'll jump into that.
All right, thanks, Chase. So my name is Stuart Ritchie. I'm the Field Engineering Supervisor for Western Canada and the Pacific Northwest. And I'll be giving you guys a bit of a crash course today on Sysmac Studio, essentially the basics and how we get programming and simulating. So a few additional Omron attendees on the call. Now, they won't all be on every call, but they should all be on one of the calls at least. So I'm sure you guys recognize either your account manager or your AE on here. Now, Chase mentioned part one. This is a 5-part series. So we have basic setup and programming. Then we're going to dive into the HMI on Thursday this week. Then next week, we'll have intermediate PLC programming, followed by networking, Modbus and Ethernet IP, and if we have time, possibly some OPC UA and MQTT. I don't have EtherCAT in there, which may seem odd to you, but it is so simple to set up that it's hardly worth mentioning. And then October 18th, we're going to have an open session. So bring your questions, bring your glitches, bring your project ideas. We'll have some Omron representatives here to talk shop with you guys. So some assumptions here. Everybody should have Sysmac installed and operational. Everyone should have some PLC experience, primarily in ladder logic. And you should be mild to moderately caffeinated. We are going to be going at a fairly quick pace, and we're not going to be stopping for a coffee break in the middle. A little housekeeping before we get going. Keep yourself muted until the question periods. Post the questions in chat whenever possible. There's another engineer on this call here who's here to help you out with those questions. And just a reminder, we have official Omron training. They're anywhere from 2 to 5 day courses. There are several under the Sysmac umbrella. This is a condensed version led by an engineer, kind of the fundamentals, enough to get you up and running, a condensed version of it. Now, on the agenda today, we'll be going over the Sysmac Studio startup screen and how we do file management. We'll walk through creating a project and selecting our hardware. Then we'll outline the software layout and the IDE, how that all works together. Then we'll talk a bit about EtherCAT, mainly just to do a quick demo on how to set it up. We'll go over some of the Sysmac fundamentals, primarily things that you might do differently on a different platform, but it's important that you know how to do them on Sysmac. Then we'll get into some programming and simulation, and we're going to be doing a pretend lift station exercise. And the idea is, at the end of this course, you'll have a project that you can open up, fire up your simulator, and you can walk through your logic, you can demo it, you can go back and check how you did something if you couldn't remember at that time. So let's get going. So the Sysmac Studio startup screen. So everyone can go ahead and open up Sysmac now. So on our startup screen, we have project management in the top left-hand side. We have the Go Online Connect to Device in the middle. And at the very bottom, we have license management. Just going to open up Studio here. So file management in Sysmac Studio is a bit different than a lot of other programs. So every project that I have on my computer currently, if I go to Open Project, you'll see a list of projects dating back to 2012 kind of thing. So those are all stored in an internal directory in a rather obscure format, and you'll very rarely, if ever, need to actually go in here. So each one of these folders is a project, but it doesn't really matter because we do all our file management from the startup screen. So if we import a project, we can grab an SMC2 project that a colleague emailed you, for example, or you had backed up to the cloud. And if we want to export a project, we could just pick on any one of these and export it. We can drop that somewhere as an SMC2 format, and then we could email that or back it up to the cloud, that sort of thing. And everything in your project is contained within this SMC2 file. So you might have a user manual on your HMI, you might have an instructional video on your HMI. Everything is contained within this project. You don't need to move an entire directory. It's all contained, bundled up, ready to go. If you're emailed the project, you can simply double click on it and it's going to open it up and bring it into your Sysmac directory. So we're always working out of that Sysmac directory. We manage all our files from within Sysmac. Now, connecting to a device, this generally is what you would do if you found a PLC out in the wild. We could also connect to drives and safety controllers as well, but today's focus is going to be PLCs. So USB, pretty self-explanatory. Direct connection via Ethernet and Ethernet connection via a hub are the two you'll probably use most. Now, if you know the IP address of the PLC, you can use Ethernet connection via a hub and put the IP address in here. If you find a PLC in the wild and you don't know the IP address, you can do what's called a direct connection via Ethernet. And as you can see in the picture here, there's a single cable between the PC and the CPU. Now we can do this option and connect to a PLC without knowing the IP address of the PLC. And we don't even have to have our computer on the same subnet as the PLC. We could have DHCP enabled on our computer and our PLC could be who knows what. It doesn't matter. We can connect to it that way. The important thing here is there's no network infrastructure in between the PC and the PLC. Some unmanaged switches will let it happen, but it's kind of a broadcast protocol. So managed switches often don't let that through. Now, as far as licensing goes, most of you are on a trial license. So if and when you were to purchase a full license, all you would have to do is click on register license, punch in your license numbers, and then you'll be on a fully activated Sysmac. We don't need to uninstall the trial and reinstall the full version, anything like that. So let's all create a new project in Sysmac. We're going to call it Lift Station. The author is going to be yourself. The category of device is going to be a controller, and in particular, we're going to use the NX102 9000. And for what we'll be doing in this program, any version will do. You could be on the oldest, you could be on the newest. It won't make much of a difference. We can go ahead and click Create. And this brings us into the IDE of Sysmac Studio. Now, the first thing I'll get everyone to do is to go to Tools, Option, and under the Ladder Editor category, make sure you check off Select Local or Global Variable and register it. And under the Variables category, select Change the variable name used in programs.
We will have this presentation slides.
Yeah, I'll pass out the slides at the end of the class today.
Thank you.
Okay, once you've closed out of that window, we can look at our IDE in a bit more detail. So we don't need to do death by PowerPoint on every one of these red boxes here, but essentially on the left-hand side, we have our Multi-View Explorer, and it's divided into hardware tools and programming tools. We have our edit pane in the middle, and we have our toolbox on the right-hand side. So depending on what we have selected in our Multi-View Explorer, the contents of the edit pane and the toolbox will change accordingly. So you can see in the slideshow here, I'm in the programming environment, the ladder logic programming environment, and my toolbox is full of programming instructions. Now, on the bottom of the page, there are what we call the accessory windows. So this is where we'll have variable lists where we can view and edit variables when we're online. We'll have cross-referencing, that sort of thing, as well as when we compile our programs, when we check all our programs for errors, any errors will be listed down at the bottom in the output and build tabs there as well. Okay, so EtherCAT, I said I would do a bit of an EtherCAT demo here. Chase talked about it quite a bit. So this project that I have is a PLC, an actual PLC sitting next to me here. I just wanted to walk through kind of the process of setting up EtherCAT. You'll be setting up your EtherCAT devices shortly here, but if we have the luxury of actually having the EtherCAT hardware in front of us, we can do what's called a compare and merge. Right-click on the master and choose compare and merge. And this will go out onto the EtherCAT network and poll for any devices that are there. So you can see it's found an EtherCAT coupler at node 11, and I can just go ahead and apply that actual network configuration to my project. And it's added it, and it's just telling me now that I need to synchronize the project. So that's how we'll add devices or I/O over EtherCAT, and we'll be doing this process for your lift station projects here shortly. And the same is the same process we follow for local I/O. So this is the CPU rack. I'll be getting you guys to manually add some I/O here too, but we can do a compare and merge here too. And this is detected I/O link master and a digital input card. So I've added that to my project. Now all my I/O is there, and everything I've added now exists in my I/O map. And we'll be touching on both of those a bit here shortly. So it's kind of the EtherCAT in a nutshell, how we do that. Now, Sysmac does ladder logic, ladder diagram, and structured text. Now, there's a nice feature in Sysmac where we can kind of have the best of both worlds and do what's called embedded structured text. So you can see in the picture here, it's on a ladder rung, but it's executing structured text instructions. So personally, I prefer to work in ladder logic, but there often come opportunities where you need to use structured text to make your life a lot easier. So operations on arrays, equations where the order of operations is important, that sort of thing. So we can actually embed structured text in our ladder logic and conditionally execute it with ladder logic conditions. Variables in Sysmac Studio. Every time you create a variable, you will get this little pop-up at the top, whether you want it to be an internal or a global. So internal, commonly called local, basically means that the program that it was made in, and that's where this blue bracket is indicating. So any one of these sections of this parent program a local variable can be used between. But if you tried to use it in a different program, up in, say, demo move here, it would not recognize that, and it would just make its own internal variable if you tried to enter the name of that variable. So global variables, on the other hand, can be used anywhere, even on your I/O map, and for networking with the outside world. Contacts and coils in Sysmac Studio. So we have in our toolbox ladder tools, which is what we'll be working out of for the majority of today. And you may have noticed that there's one input and there's one output, commonly called a contact and a coil. So if we right click on either of those, that lets us change the type of input or output that it is. In Sysmac, we call rising edge instructions diff. So rising edge up, rising edge down is diff up, diff down. Invert would change this input to a normally closed. And if you're a hotkey programmer, invert is just /. Timers in Sysmac Studio. So we utilize the IEC 611 time data type. It's the same way that it's specified in the standard. So when we're typing constants for time, we specify them as T, pound, and then the days, hours, minutes, seconds, and milliseconds that we need. So in this example here, this is my New Year's Eve countdown, 62 days, 6 hours, 23 minutes, and our lapse time is given in the same format. So if you ever need to write to that with milliseconds, for example, there's a little snippet here from the help file. That's in the help instruction for all of the time related instructions. So that's not something that you have to screenshot or anything like that. Constants in Sysmac Studio. Most constants need a data type specifier in front of them. So in my example here, I have real pound 3.14159. If I just typed 3.14159, I don't think it would like that very much. So it's good practice to type the data type in front of it, followed by the pound, and then the actual value. Now we can also express constants in binary or hexadecimal as well. And to do that, we type the data type, we type the number base. So 16 would be hexadecimal, 2 would be binary, and then we can specify that number in either binary or hex. Tag attributes. I promise we're almost done the PowerPoint section here, guys. Tag attributes. If you open up your global variables, which we will be soon, you'll notice some possibly unfamiliar attributes for our tags. So we're just going to touch on these very quickly here. So initial value, that's pretty self-explanatory. So on before the logic starts running, the very first value that's written to it is initial value. It's completely optional. The at column, the AT column here. So this is where we can either assign an address to it, or it will tell us where in our system, either on a remote rack or on our local rack, this is mapped to in our I/O map. So this is done automatically. We don't need to create this syntax here. It's just kind of a reminder that this is used here. The retain attribute, pretty self-explanatory. If that's checked off, it will be retained through power loss. And if it's a constant, then it will not let you logically write to it. Your program will not compile if you try to write to a constant. Network publish, we'll be covering a bit more in the communications one, but this basically is for OPC UA and Ethernet IP. The majority of your tags are going to be do not publish, and that's also the default. And one last thing, F1, when you click on any instruction, press F1 and it will pull up a very detailed help document on that specific instruction with all the information you could want, as well as programming examples in both ladder logic and structured text. Okay, so we're going to get programming here. Does anybody have any questions on kind of what's been covered so far? Okay. So this is what we are going to be programming. It's a lift station. It's going to have a main PLC in the control room, and it's going to have a remote rack out by the lift station itself. And as far as devices go, it's going to have a level transmitter, It's going to have a pump with run feedback. It's going to have an alarm beacon. And then it's going to have 2 illuminated push buttons and 1 standard push button back in the actual control room. Now, you guys don't need to screenshot this. It's in the student files if you want to go back to it. This is just kind of tells you where everything is mapped out. So the first thing I will get you guys to do is add an EtherCAT device. So we can double click on EtherCAT in configurations and setup. Now, once you double click on EtherCAT, the contents of your toolbox have been populated with categories of devices as well as the devices themselves. So we're going to go to terminal coupler. This is the remote IO coupler over EtherCAT. And I'll get everyone to drag and drop an ECC 202 on top of their master. And that should auto assign it node address 1. Then I'll get everyone to right click on it and choose Edit Slave Terminal Configuration. And on our remote rack, we are going to have 3 cards, an IA3117, an OC2633, and an AD2203. This is a digital input, a digital output, and an analog input. And I've chosen the first cards that are in that list when you click on that category. So digital input, we can either drag and drop or double click on the card we want, and we can drop it on our coupler. Digital output, we'll grab the first card from there. And then analog input, we'll grab the first card from that list as well. Give everyone a second to do that. So next, we're going to add some local I/O to our PLC. So if we click on CPU and expansion racks, and then double click on our CPU rack, this will bring up the local rack. Now we're going to do a digital input and a digital output card, the same ones that we used before. So our digital input card will be the IA3117. Our digital output card will be the OC2633. And I'll give everyone a second to do that. Okay, so we've added all our I/O cards to the system. And the next step we need to do is we need to assign variables to those I/O cards so that we can use them in our logic. So if we go into our I/O map, which is right below the CPU rack, we can drill down to each one of those cards, and the variable column will be where we create the variable that we want to use for them. It will automatically create it as a global variable when you type it in the I/O map. And you don't need to put the variable comments if you don't want to, but this is what the I/O map will look like when everything is tagged. So I'll leave this on the screen for a minute here while everybody copies all those tag names onto the variable column. And if anyone's having any issues, feel free to speak up now. We can help you out while we're waiting to do this. Hey, does anyone need another half a minute here?
Yes, please.
Okay, no problem. Okay. So this is the control philosophy for our lift station. And this is also located in the file that I sent out to everyone, the student material. If we go to session 1, both the list of the IO map and this control philosophy and some of the pictures are in the lift station slides here if you want to go back and reference it. But essentially, we are going to go through these one at a time. And once we get about halfway through, I'm going to kind of let you guys have free reign. But the first couple we'll walk through as we explain the programming environment and some of the ins and the outs of Sysmac Studio programming. So number 1 here, it says at startup, and in brackets, P_first run. So this is a system tag that's true on the very first scan of the PLC and the very first scan only. So you often use this to do things initially. So this will place the plant in stop mode. The run mode tag will be false. So let's do that logic first. So we have a run mode tag and we have our first run bit. So I'll get everyone to go into Program 0, Section 0. You may need to expand yours and drill down to it. But we have a blank rung. Program 0 and Section 0 are in every project by default. And on the right-hand side, we have our toolbox. So we have every single instruction that's built into Sysmac Studio in the right-hand side in the toolbox here. Now, the primary ones you'll be using are going to be in ladder tools. So this has a generic function block. Function versus function block is a bit of a discussion for another day. We have our inline structured text that we talked about earlier, and we have an input and an output, as well as a branch. So I'll get everyone to drop an input onto their first rung and drop an output onto their first rung. So they come up without any tag names in them. Now Sysmac will autofill whether it's a user variable or a system variable. So if we type P_, you can see we have a few different options here. We have an always off tag, an always on tag. We have first run mode or first run. I'm going to use P_first run. And then on my output, if you remember from the control philosophy, there was a tag called run_mode. Now, because it's never seen this tag before, it's going to prompt me 2 things. The first is whether this is an internal or a global variable. Make everything global when in doubt, because we're going to be using most of these on the HMI, and they'll need to be globals to be used on the HMI. And then it prompts you for a comment. Now, if it was unsure of the data type, which will happen on instructions that take multiple data types, there would be an additional pop-up for a data type. But because a coil can only be a Boolean, it's automatically made that a Boolean. So.
Hey, Stuart, because Teams chews up some of our monitor space, can you zoom in on the latter portion just to make the text larger?
Absolutely.
Just a tip for anybody who is having trouble seeing, if you go to the More icon up at the top, and just make sure you're in full screen, and then check Focus on Content, and it should increase a little bit of your visibility. But yeah, you're right, Jay. It's can be a little tough to see.
Stuart, click on the rung of ladder, and then do your zoom. Thank you. Perfect.
Now we're going to right-click on this run mode coil that we made, and we're going to make this a reset instruction. So plant is operational when this is true. When it's false, we're in stop mode is basically what that means. So we want to make that a reset instruction because we're going to be using it in multiple places. And the next item we have, so the start push button will place the plant in run mode as long as the level switch low isn't tripped, which will make run mode true. So I'm going to insert a rung below, or if you're a hotkey programmer, that's R. And our start button we have already tagged. So that's, oops. I didn't tag them on this one. That's right. Oh, that's all right. You guys should already have those tagged. I'm just going to pull up the tag list here on my other monitor so I can make sure I get them right. Okay, so if the start push button is pressed and we don't have our level switch low, meaning there's water in our tank, we can go to run mode. So the way this level switch is, kind of our imaginary level switch is when the contacts are closed, so when there's a 1 coming back on that input, there's water there. So that will be a normally open. That'll be our level switch low. So if both these conditions are met, we're going to add a coil, and then we can set our run mode. Okay, so I'm pretty confident in my logic at this point, but I want to be sure. So one thing we have in Sysmac is a built-in simulator. So up at the Windows menu at the top here, we have simulation run. So this will build a virtual PLC for us, and this will let us run our logic like we're online with an actual PLC. The look and feel will be identical to being online with an actual controller. The first time you do it, it takes a bit longer, but sequential times, you're just starting and stopping the simulator. You're not building it. So here I am in simulate mode. So if we want to change the value of a Boolean variable, we can right click on it and choose set reset. Or if we double click on it, we can simply change it from true to false right there. So we're gonna have to set our level switch low, low, true a number of times whenever we're simulating here. So our start push button, we can test that. Turn it off, and you can see that our run mode remained on because that was a set instruction. I don't think we can force first run. No. So that worked. Is everyone's simulator operational? Okay, I will assume from the silence that it's working for everyone. That's good. Now on the right-hand side, once we fired up that simulator, down at the bottom, a simulation pane became visible. So all we have to do now is just stop our simulator. The next time we want to run it, we'll click play so we can make some logic, simulate it, stop it, make some more logic, etc. So the next thing from our control philosophy, we've got 1 and 2 out of the way. Now, while we're in run mode, the pump will turn on when the water is above the high set point, and that's this high set point tag we'll have to make. The pump will remain on until the water is less than or equal to the low set point, which is LO_SP. We'll have to create that tag. So pretty simple start stop level control. I did miss something in that control philosophy. We're going to want to be able to stop this as well. So we'll do a similar run to number 1 here, and this will be the stop push button. Will actually stop the plant. We'll reset run mode. So I'm just going to cut and paste that instruction here. So if for some reason we need to stop, we can press our stop push button, or the level switch low low will also kick out our run mode. So to make a branch, an OR condition, there are a few ways to do it. The easiest I found is to copy the tag that you want to branch and paste it on top of the tag that you want to branch it with, the instruction you want to branch it with. And you can see it's already automatically made that OR instruction. And I'll just have to invert that. And now my stop push button, or if I run out of water, that will turn off my run mode here. Sorry, that wasn't in the control philosophy there. So now we'll move on to the level control here. So we turn the pump on whenever the water is above the high set point. We turn it off whenever it's below the low set point. So we're going to need some comparison instructions. If we go into our toolbox under comparison, right at the very top, we have less than or equal to, not equal to, greater than, and greater than or equal to. So we'll want greater than or equal to while we're in run mode. And we're going to want to make a tag because we don't have that set point tag. Now, when I mouse over this comparison instruction, input number 2 or input number 1, the type in the little tooltip says any elementary data type, except Boolean, of course. So that doesn't have a defined data type. So when I type my high set point tag, it's a new tag, so it's going to ask me internal or global. We want it to be a global. Now it's going to ask me the data type. Because this will take any data type, it has to check with us in order to know what data type it takes. Many instructions take only specific data types. So if I were to make this tag on an instruction like that, it would not prompt me. But because it takes any numerical data type, essentially, it's prompted me. So I'm going to make this a real. And we will put our tank level raw tag in there. Oh, sorry, no, that's not going to work on yours. We need to scale that into a real. That's an integer. Yes. So in Sysmac, we do need to be cautious of data types. So because I was making that tag, I could make it a real, but you guys, when you created this tag, you made it an integer. So we need to actually scale that first, like you would with any analog device. So what I'll get everyone to do is add a section to your programs. And it created section 1 here. I'm just going to rename this analogs. I'll get you guys to go inside of that, click on the rung, and press I, which puts a function on the rung. That's also in Ladder Tools function. You can drag and drop it from there. And if we start typing scale, a scale trans instruction comes up, scale transformation. This is what you would use to scale an analog input, the raw value to a scaled value. So we need to convert. This works with the real data types, and our analog input gives us an integer. So we also need to convert our, oops. We need to convert our raw analog signal into a real in order to use this. So a raw analog signal is an integer. So int to real. Now we can put our tank level raw in there. We can output a tag called tank level real. Now we can use our scaling block to scale this to 0 to 100% for our tank. So how this scale transformation block works is it has x0 and x1, y0 and y1. So x0 and x1 is the raw value minimum, x1 is the raw value maximum, y0 is the scaled value minimum, y1 is the scaled value maximum, and offset is just an offset you can put on it if that were in a non-zero place at the base. So these will just be constants because we know the analog card resolution. So I'll put in real pound 0, real pound 0. They're both 0 based. Now our analog input is 0 to 8,000. Real pound 8,000. And we want to scale that to 100%. And then our output here is going to be tank level scaled. And we'll have to make that a real.
Can you zoom in on that one again slightly, Stuart? Thank you.
No problem.
Hey, Stu, just real quick here. For your X1, why is it 8,000? I think I may have missed that.
So the resolution of our analog card is 0 to 8,000.
Oh, right. Okay.
Yeah. And if anyone's curious where I got that number from, when I dropped that card on my EtherCAT coupler here, let's go to the analog input devices. So when I click on it here, there's a little tooltip down at the bottom that tells me what it is, whether it's 0 to 10 or 4 to 20, and it also gives me the resolution. So 1/8,000th right there. So that's where I got that 8,000 from. So I'm going to simulate that to kind of illustrate how this scaling function works here. So when we're running the simulator, if we want to change the value of a numeric variable, we can double click on it and we can write a value to it. So 0 to 8,000 should scale to 0 to 100. So if I typed 8,000, that's given us a scaled value of 100. And if I were to type 4,000, that should be 50. And it should be a linear relation the whole way through. So our scaling works well. Does anybody have any questions on either the scale transformation block or anything we've done so far? Okay. Yeah, sorry, we should have done that one first, but you know, that's programming for you. Sometimes you backtrack a bit. Now, back to our control philosophy here. So we have our tank level scaled that we're going to be comparing with our high set point. And there's a number of ways you could use this logic, like achieve this operation. If you like to do it a different way, you go right ahead. I'm just going to do it the first way that comes to mind, which isn't always the best. So when it comes time to simulate this, it's going to be a bit of a pain in the butt to go back and forth from analogs to section 0 to analogs, change your tank level, then go back to section 0 and see if you got the desired result. So one thing we're going to use now is called a watch window. So we'll go up to View, Watch tab Page. There are two here. There's Page and there's Page with table in brackets. So Page with table in brackets is what you use when you want to look at a structure or an array and see all the elements inside of it. If you're looking at a single data type, we want just the Watch tab Page. So down at the bottom, that popped up this window here and I don't think I can make this one any bigger, sorry. But under name, we're going to type tank level raw. Now that's going to always be at the bottom of our page now. So when we're simulating this, we can just modify our analog input here, and we can watch the logic happen, and it'll save us a lot of back and forth in between the two programs. So I'm going to go ahead and start my simulator and see if my tank level logic is functional. Now the high set point and low set point are going to be 0. So the first thing I'll have to do is assign set points for them to work between. So I'll say my high set point is 80%. My low set point is 30%. Now I'll put my plant in run mode here. So now you can see the power flow on the rung is waiting for our scaled tank level to rise above our high set point. So if I go down to the watch tab that I just dropped down there, I can assign some values to this. So I'll go to about 50%, which is 4,000. And that should not turn on the pump, which is correct. Let's go to 75%, should be 6,000. Did not turn on the pump. Now I'll go to 7,000, which turned on the pump for me. Now I'll slowly drop the tank level down. You can see my my sort of relay logic latch bypassed the first greater than or equal to. And I need to get below 30 now to turn off the motor. So I'll keep dropping my analog input down. 37.5%. And at 25%, it has stopped. So is that working for everyone? Is anyone having any issues with that? I'll stop my simulator. I will go back to the control philosophy here. So item number 5, in the event that the level switch low is triggered, stop the plant, turn on the beacon, and flash the red LED. The red LED is on our stop push button. That's one of the outputs that we created. And we're also going to make a tag called LSLL_alarm. Oops, go back. Okay, so I'm going to leave this up here for a few minutes, and you guys are going to take the reins on this one. You'll have to create a tag for the LSLL alarm. This will be latching because we want to know if this went off, even if the water has rised above the low level switch. We want to know that it happened, so we'll latch that tag. And we also want to trigger the beacon and turn on the red LED. I will help you with the flashing part, but I'll give you a few minutes to proceed with that. If you have any questions, by all means, say them now or type them in chat. I'm going to cheat a bit here. I have a finished program. I'm just going to drop my variables in here. We're going to be doing some exercises like this in the day 3 courses. And for that flashing condition there, Sysmac has various time clocks available to you. So I'm just going to put a function on that rung, and it's called get. And you can see here all the different time bases we have, and I'm just going to use the 1 second clock. So that's on for half a second, off for half a second, and that will flash our stop LED. Now we'll need a way to reset that alarm in the event that it did happen, because our plant won't run with this LSLL alarm on. So I'm going to use the reset button to reset our alarm if the level switch is cleared. I don't have anything in the control philosophy about this. This is just kind of what you would do in practice. So I'm going to run my simulator now, test out what I've made so far. So I'm not going to go through the process of starting the motor and everything like that. I'm mainly concerned that if I turn on level switch low, I set that alarm bit, even if we lose it, my alarm beacon has turned on and my stop LED on the stop push button, the red LED is flashing. And if I want to reset it, once that level switch has water above it, if I hit the reset button, the alarm is cleared. So that tested out okay. Is anybody having any issues? Any questions? Tomorrow, we're going to be building an HMI project where we'll have a graphical interface that works with this logic. So when we're doing our simulations tomorrow, we'll actually have graphics for our lift station, and it'll be much more appealing to the eye.
Hey, Stu, we got a question here from Jake.
Okay.
He's asking, shouldn't your high set point comparison be a less than equals to?
If it was, sorry, my high comparison, let me just check this question here.
No, I think it's correct, Stuart. Your intention is when the level goes above the high set point to go ahead and turn on the motor.
Yes.
Correct? Yeah. So it should be, it is correct.
I know it's a bit confusing because I'm using two high set points. So I could see that being a little confusing, but if this was a low or this was a low, I don't know if it would work.
Is your low
My-
correct? Go to your second comparison, the comparison to the low. So you're saying that if the tank level scaled is above low, let it on. It shuts off when it drops below. Got it.
Yeah. This is kind of why I gave everybody on the call kind of the freedom to do it how you wanted, because this way might not be the way you want to do it. We could have a greater than setting start motor. We could have a less than resetting start motor. That might make more sense logically. But so as long as we're above the low and above the high, then we can start the motor. This start motor branch here will bypass our greater than or equal to once we sort of fall below that. You can see now we're below that, but we're being held on because of this start motor. And then once we drop below our low, then that will turn it on. So I guess the downside with this one is if you started somewhere in the middle, you'd have to wait until it gets above the high set point before it'll turn on. So always multiple ways to program things. I think I do have my level switch backwards though. So one thing I haven't touched on is online edits. So if we right click on the rung number and we go to online edit start, and this is identical to doing it on an actual PLC, you can see the logic in the background has turned to white, and that's the entire program. So when we do online edits, it's not just one rung at a time, it's the entire section at a time. So I was going to invert these. I got my normally open, normally closed mixed up there, but then when we're done, we go to online edit, transfer.
No, hang on. You don't want those last two inverted. You don't want the alarm inverted.
Oh, right. Yeah, not the alarm. Good call. Okay. So is everyone ready to move on to our next control philosophy point here? So when starting the motor, if we don't see run feedback within 700 milliseconds, stop the plant, trigger the beacon and flash the red LED, just like we do for our low level alarm. And the tag we're going to make for that is motor underscore FTS, failed to start. And we're going to make that alarm bit true. So the logic is going to be fairly similar to our level switch, but we need to incorporate two conditions, and we also have to have a time delay in there. So I'm going to stop my simulator. And I'm just going to kind of inject this logic right in the middle here, where we turn on, right below where we turn on the motor. And again, if you guys would like to kind of do this your own way, you're more than welcome to. The control narrative is in the student material in the lift station slides. So by all means, if you've got your own way you like to do fail to start alarms, then you go right ahead. And for my timer, we have a category called timer, which has our different timer types. And we'll want to, I'm going to use an on delay timer for this. It's TON if you just wanted to type the name of the function block. Now with function blocks, we do have to give them a name. Functions we don't, function blocks we do. And for the time set time, which is PT, I'm not sure if you remember from the slideshow, but when we hard code a constant for time, it's the syntax is T pound, and then the time, in our case, is going to be 700 milliseconds, ms. We don't really care about the elapsed time, so we can leave that blank. And we'll, of course, give ourselves a way to reset that alarm bit so we can try to start the motor again. So I'll test that part by firing up my simulator. You guys will probably be pretty familiar with this process now. So you can see right away, I got my motor failed to start alarm, which is correct because I haven't, I'm going to have to force this run feedback in order to disable that alarm. So that pretty much confirmed it right there. So the run status and the level switch, you're going to have to force quite often when you're doing your simulations just to get by, avoid the alarms kind of thing, which is true in commissioning quite regularly. So now I'm just going to duplicate what I did with the low level alarm as far as the beacon and the stop LED goes. I think we're confident enough in our beacon and our stop LED that we don't need to test it for that condition. So we'll take a look at the narrative here again. So the reset push a button will clear the errors. We've kind of been doing this on the fly, which is correct. That's done. Now the LEDs on the button and the beacon will reflect the mode. So this is something we haven't done. So when our plant is operational, our green LED is running. When it's stopped, our red LED is solid. And when it's in alarm, our red LED and the beacon are on, the LED is flashing, which we have. So we haven't done anything with the green LED yet. So we'll need to add a rung for that. Run mode. And the start LED is our green LED. Now for our stop LED, we're going to have to do some branching and some additional logic to get this to behave the way we want. So you guys are more than welcome to do this the way you want to do it. I'm going to take a crack at it myself here. Okay, it's not the prettiest run, but I think that's going to accomplish it. Test it out. So we're currently in run mode. Green LED is on. We hit the stop push button now to take us out of run mode. Should I turn that off? Okay, so stop push button has held the LED solid. Now, if I was running, that got my level switch low. My red LED is flashing. And I'm confident enough in this rung that the motor alarm will do the same thing. So I didn't add that to the beacon, I don't think. Nope, they're both on the beacon. Yep. So yeah, that is the control philosophy done. So we've got about 8 minutes left here. Is anybody having any trouble with anything in the software? Any questions on what we've covered so far?
We will get the presentation and the video of this presentation, yes?
Yep. Correct.
Perfect.
And
because
I'm
I need to revise it, yes.
Yeah, absolutely. And I'm also going to send out a Sysmac project, basically the one I've worked on here, just a bit better commented. I've done it in advance. So I'll distribute that if there's any part of it you want to look through in the actual software to see how we did something. I'll be doing that at the end of each each day as well. So
Yes, perfect. Because we are in the work, so I can focus 100%. Yes. Okay.
yeah, hey, that's life, no problem.
Hey, Stu, could you scroll up just a couple rungs there?
Whereabouts? Did you
Just
wanna go?
one more. I just want to see the motor feedback. There you go.
Oh, okay. Yeah, so the idea with this one is this will be true when the contactor has engaged. So if we're calling for it to start and we don't see that contactor pull in, we give it 700 milliseconds and then we trip the alarm. I'm going to load up a bit of a teaser for what's coming tomorrow, also to help you guys kind of visualize what this list station's doing in the real world here, in the real fake world.
Now for the intermediate programming, or I guess it's not really that intermediate, but cycling back and forth between pump A and pump B. Real life
No, we're
lift
not going to
station.
do a lead lag on this one. We will be making our own function block, two of our own function blocks based on the logic we've already created.
Yeah, if anybody has any other questions or comments, feedback, feel free to either put them into the chat or email me after the session. Me being Chase Miles. Hi, Eddie. We have sessions running Tuesday and Thursday. So this Tuesday, obviously, was this session 1. Thursday is going to be session 2, which I believe is that going to be the HMI stuff, Stu?
Yeah, sorry if I said tomorrow, I meant Thursday. It's correct, Jay. And yes, so Thursday this week will be the HMI stuff. And then next week we're going to have intermediate programming, where we're going to kind of incorporate some of the more advanced features into our lift station PLC. And then the Thursday on that week is going to be about communications.
And then we will be having one the following week. It's not going to be a full session. I think it's on the 18th. That's just going to be bring your scenarios, bring your questions, comments, and we can kind of have some free time to hash some stuff out. I think that's the 18th.
Hey, well, we're wrapped up on the PLC stuff then, guys. I will be sending you the PowerPoint, a Sysmac project, and a YouTube video link of what we covered today if you wanted to go over it or you had any questions. So I'm going to stay on for another few minutes here if anybody has anything they want to talk about. Otherwise, feel free to jump off, and we'll hopefully see you on the next one.
Thank you.
Yeah, thanks, Stuart.
Thanks for attending, guys.
Thank you.
We'll see you on Thursday.
Thank you.
Thank you.